Okay, I'm glad to present you our colloquium speaker today, Erik Verlinde from the University of Amsterdam. Erik did his undergraduate studies in Utrecht. He did his master thesis with Gerald Hooft, and then his PhD thesis with Bernard de Witt. Then he went for a postdoc position and some temporary positions in Princeton in the Institute of Advanced Studies. And after that, he came in '93 at CERN as a permanent staff member for 5 years. And at the same time, at least part of this time, he was also professor in University of Utrecht. Finally, he have chosen not to stay at CERN, neither to Utrecht. He went back to the States, to Princeton, where he had a professor position for 4 years until 2003. And then he decided to come back to Europe, to Amsterdam, where he is until now. So Erik is an expert of string theory and quantum and gravity in general. And recently he has some new ideas of how to think about gravity that he is going to talk about them today with the title, The Common Origin of Gravity, Dark Energy and Matter.
Thank you very much. Well, first of all, it's a pleasure to be here at CERN and to be able to talk about these ideas on gravity. I'm going to talk about work I did, well, it's based on work I did more than a year ago, but I'm also going to add things that have been worked out after it. So this talk is going to be basically two parts, where first I'm going to introduce the general idea of why gravity may be thought of in a very different way. And then I would like to add new insights that you can get from that in the nature of, well, things like dark energy. I mean, things like dark matter. There are all kinds of puzzles related to gravity that one would like to understand better. And I'm claiming that by thinking about gravity in a different way, we can gain insights into those questions. Our usual way of thinking about space is that it's a stage on which matter moves under the influence of forces. This is the way in which Newton started developing physics, and we still think about it today. Here at CERN we do the same thing. We think about particles and their forces, and this is the way in which we can organize the laws of physics. Gravity I put outside of there because in a certain way it doesn't really play a role when you do your experiments with particles, and although there's some speculations that it may become important, I think gravity is really a separate issue from all of the fundamental interactions among particles. But the idea that space-time plays a role in gravity, that of course goes back to Einstein, and that is also what makes gravity very special. There's another way in which the gravitational force acts. Everything that has an energy is attracted by gravity. It's much more universal than any of the other forces of nature. And there's a good reason why it sort of doesn't fit into this, because precisely it is related to, it doesn't fit very well in the standard model, is because it's related to space-time. And the way we have to combine it with quantum mechanics also has to tell us something about what space-time is. So it also goes back to the origin of the universe. If you think about the equations that we use there, they're gravity equations. And so we have to think about what made forces originate, matter forces and everything like that originated at the same time. So our current paradigm is based on the idea that forces are mediated by particles, and so for every fundamental force we have a particle, and gravity would then have a graviton associated to that. I think that paradigm will eventually change, because it first of all assumes the presence of space-time to begin with, and certainly there's other ways in which forces can originate. And gravity actually is the main force which already starts to show signs of being emergent in another way. So I'm going to use ingredients from various sites, theory as well as observation. I'm a theoretical physicist, so I'm using a lot of intuition that comes from theory. In particular, string theory, we discovered a lot of things. I'm going to explain a little bit of that. Black holes also is a very important theoretical laboratory to think about questions related to gravity and space-time. But also the observations. If we look in the universe, we see that 96% of the energy is really in forms that we don't understand. Dark energy and dark matter are really puzzles if you think about our laws of physics. And I know, of course, many people eventually would like to discover what a dark matter is, but I think and in particular if it could be some particle that could be discovered here at CERN. But without understanding also what dark energy is, I think there's still a big theoretical problem there. And this problem that we don't really know how to describe this big, 96% of the energy, is an indication that our laws of physics may not be sufficient to describe them yet. So I want to change the way we think about it. And there may be actually a good reason why we don't understand it. This is the picture. I'm going to get back to this at the end of the talk, because I'm going to indeed present some new insights in this matter. So this is string theory. String theory sort of works on a very similar idea as particles, except that we replace point particles by vibrating strings. But it's still vibrating strings that move in space-time, and they can exchange from one to the other, and so we can mediate forces by having one string being emitted and being absorbed by the other. And then if you do this with closed strings, you notice that there is a state there that would behave like the graviton. This is why string theory contains gravity. But if you really ask string theorists, do we know what string theory is? Not really, because this is a perturbative picture, and we are on our way to discover much more about it and understand where this perturbative picture comes from. There must be some underlying formulation which indeed should make clear what really the space-time looks like. So at the end, I will present more of what sort of the emergent picture of space-time would be that comes from string theory. But this should be thought of as really more of a perturbative way of thinking about it. So a big discovery in string theory is this idea of D-branes. So D-branes is an idea that there are other objects than just vibrating strings. They can be extended. And for all we know, we might be living on a D-brane, and this is how the ideas of sort of extra dimensions can come in, where gravity then lives, because gravity is associated with these closed strings. Those closed strings, they can move off the brane, while the open strings that carry the gauge particles are connected to the D-brane. So part of what I'm going to say about gravity is related to this picture, the fact that gauge particles are like open strings, and that closed strings carry gravity already is an indication about the emergent nature of gravity. Because if you think about these D-branes, this is the slide I want to show. If you think about D-branes, they can also have forces between them, and they can be mediated again by a closed string, for instance, that goes from one side to the other. So that would be the graviton going from one D-brane to the other. But you can look at the same picture in a different way by thinking about the open string that goes from one D-brane to the other one. And then it's a one-loop amplitude in the open string that's the same as the exchange of the closed string. So open strings, as I said, are related to gauge particles. So this is a loop amplitude for, so let's say, gauge particles, but maybe many more particles, because open strings generally contain much more. But the graviton is then sort of the effect of it. So there's one way to think about gravity exchange as integrating out certain degrees of freedom. String theory already tells us that there's a way in which gravity can be induced by integrating out other degrees of freedom. The fact that a quantum effect in this direction becomes a classical effect in the other direction, because, well, this is a tree-level diagram, and this is a one-loop amplitude. So there's a certain way in which quantum effects and tree-level results can be exchanged. And gravity then is the classical gravity can just be understood as a quantum effect in the other channel. And now this is a hint from string theory, and I'm going to take this hint seriously, because there are many other reasons why gravity appears to be an emergent force. And the other ingredients have to do with black holes. So just to tell you what I meant with emergence, so emergence to me is also a consequence of the way we do physics. We do physics by describing what we see, phenomena, and we use the variables that we use in our daily lives and even in our detectors and so on. But the microscopic physics that's underlying it, we don't really know what it is. And in general, we have to forget about a lot of it. We generally forget a lot of information and a lot of microscopic details. What can happen is then that when you average over all of these microscopic details, certain phenomena can emerge. Like temperature, for instance. Temperature is a notion that we introduce for what we feel on our skin, but if you think about microscopically what temperature is, it's just an average of the energies of all the particles that are moving in this room. So temperature is an emergent notion, and gravity very much like this. So the picture here I show is that microscopically you don't really see what's happening, but if you look at macroscopic scales, you might see a picture where you start emerging things like mountains and so on. This is actually a pixelated part of this whole picture in here. So microscopically, the things that we've introduced macroscopically, like mountains or in this picture, microscopically they may not exist. So at a microscopic scale, we may not be able to use the laws of gravity as we use them today. So that's at least the concept of emergence in my, here I said that we use macroscopic phenomena, microscopic scales, which in microscopic scale, these phenomena may not have a meaning. So I'm going to get now to black holes. So black holes are objects where the matter is so much concentrated that light cannot escape. And for us theorists, it's very nice to think about them. In particular, the fact that they have a horizon plays an important role. So horizon is the surface from where light can no longer escape. And that's a distance away from the black hole that's related to the mass. This is called the Schwarzschild radius. And so you can think about the surrounding black hole as something surrounding the black hole, which is called the horizon, as a surface, and everything that's contained inside of it is invisible for someone that stays outside, because no light can escape, or even no signals can go from one side to the other. So this is a space-time picture of a black hole, and a black hole has this horizon in the middle, this circle, and you can think about the black hole as, the horizon as follows. If you have light signals going in all directions, generally this is what happens, but when you have a light emitted from the horizon, it cannot travel outside, it only goes inside, and also the colors change, and even clocks start slowing down. So on the horizon, there's no time basically stops, and energies get redshifted, and eventually nothing can be seen coming from the horizon. So that's another way of thinking about horizons in a space-time picture. Now, the kind of thought experiments that people started doing with this revealed a lot of things about space-time, but also about matter. And they go back to the 70s. I'm going to mention Hawking in a minute, but Bekenstein was basically the one that sort of started with very clever thought experiments, and in particular one that gave important insight. So the kind of thought experiments that people did was thinking about a particle that you lower towards the horizon while extracting the energy. So you attach it to some fictitious rope, and you let the force do work, and then when you lower it very slowly to the horizon, on the horizon the particle doesn't have any energy anymore, so the mass of the particle has disappeared. And if you then allow the particle sort of to drop into the black hole, nothing really changes to the black hole because the energy is gone. So you've transferred all of the energy contained in the particle, the E equals mc squared, into work without changing the state of the black hole. Now that cannot be because of thermodynamics. Indeed, if you would do it with a box of radiation or some particles which have a finite entropy, you would run into problems with the laws of thermodynamics. So Bekenstein saved this by saying, well, you cannot really put the particle on top of the horizon. There's a small distance away where you have to sort of declare that the system of particles that's inside the box and what's making up the black hole are basically the same. And then there's a little bit of energy left, and if you throw that into the black hole gets bigger, and then something changes. And you would like to save then the law of thermodynamics by claiming that the amount of entropy in the box somehow gets captured by something in the black hole. And this is how he discovered that the area of the black hole is basically associated with this entropy. So it's entropy then should be thought of as the amount of information also contained in the black hole. So this is black hole entropy, which eventually was made more precise together with Hawking, and so it's usually referred to as the Bekenstein-Hawking formula for entropy of a black hole. So you think about the horizon as a place to store information, and there's one bit of information on every Planckian area surface on the horizon. And so it grows like the area in Planckian units, in natural units. And so this is a measure, as I said, for the amount of information inside a black hole. So it doesn't grow like the volume, it grows like the area. And that's quite natural because this is this horizon. So I already mentioned Hawking, and Hawking discovered that black holes don't have just entropy, but also temperature. And I'm going to tell you about this temperature and write it in a particular way. So the way it arises is because there are quantum effects near the horizon, particles being created, and antiparticles, and then one particle drops in, and you get this Hawking temperature. And I express it in terms of the acceleration on the horizon. And so this is all, again, in natural units. Well, the constants of nature I've added in here just to make it explicit. But the acceleration then just follows from the usual Newton equation for the gravitational acceleration on the horizon. The reason for writing it this way is because there's another effect which is unrelated to gravity, which also has a temperature associated to it, which is due to Unruh. And here I should be another picture. I mean, namely, if you look at the horizon of a black hole, this is a space-time diagram. It sort of looks the same as what an accelerated observer would see just in empty space. And there's another temperature called the Unruh temperature that only depends on the acceleration of that observer. And so also an accelerated observer will see radiation. And actually an accelerated observer also has a horizon when you keep accelerating. I mentioned this because I'll use it in a minute. Anyhow, the whole idea of black holes having thermodynamical properties led to a discussion between Hawking and many other people, in particular about the quantum properties of black holes, and maybe about the information that you throw into a black hole, whether that can be retrieved, yes or no. In particular, do black holes obey the law of quantum mechanics? Because quantum mechanics will tell you that information gets preserved. In particular, at Hoofd, my advisor, who actually made a strong case that quantum mechanics works and there's no way you can even think about destroying this information. And this led to a very important idea, namely that the amount of information that you can put inside a certain part of space can never exceed the area of that. And the reasoning was as follows. He said, well, if we assume indeed that black holes have an amount of information proportional to their area, if I have another part of space and I start putting in information in there, that information is also associated with energy, and eventually the maximal amount of information that I can put there will be when I start forming a black hole in there. So the black hole is really the state of maximal information inside a certain volume, and then the amount of information should grow like the area. This is a very important idea because it means that the information that you have, say, inside this room can never be more than what you can write in terms of as bits on the surface. This is why it's called the holographic principle, because you have to reconstruct what's going on the surface from the information on the surface from what's going on inside. Which, by the way, I think for experimentalists in high energy physics is something they do every day. But I'll make a reference to that in a minute as well. So anyhow, so the information that you think about should be thought of as really information then on the boundary. Well, this seems like a sort of far-fetched idea, and at the moment that it was proposed, it wasn't really clear that it could work. But one of the nice things that happened in string theory is that we have been able, using D-branes, to count black hole states and make indeed contact with this whole holographic principle. In particular, we have been able to find an example of this holographic idea using ADS-CFT. I mean, this is a development. It's called anti-de Sitter conformal field theory correspondence. I'm not going to say much about the details, But just the idea that there is indeed a duality, a relationship between something where you put the information on the boundary and another description of the same system which has one dimension more, that is, well, by now established quite a bit because it's already an idea already 13 years ago it was proposed. And so what happens here is that we have some microscopic description in well, bits or some kind of, well, it's actually field theory living on this part of the diagram. So this is the boundary of the space. And then there's an equivalent description of the same physics where you add one dimension, which is the orthogonal here, and then you take gravity inside this, this space. In particular, you can put a black hole there. And if you put a black hole there, it has a temperature. And that temperature you can associate with the temperature on the boundary. Basically, this construction used the idea of D-branes because you can think about this D-brane as being describing the boundary, and the gravity in the bulk is precisely what's described by those closed strings. And so people work this out, and one way, by the way, to think about this additional dimension is as the scale, the size, which has to do with the energy scale or even the size of objects on the boundary. And I'll use this in a minute. But in particular, we can put a black hole here and do, for instance, our thought experiments that we described before. If you do that, you can take a black hole in this anti-de Sitter space and think about this particle being lowered towards the black hole horizon. This direction, by the way, is then the perpendicular direction which didn't exist on the boundary. So it's a direction here which is the emergent direction of the space, because if you think about this description, it's really holographic, so it has only the boundary, but then somehow there's another way of thinking about it where you add one other dimension. And so you can ask the question, what does this experiment, this thought experiment, look like from the other description? I told you that the black hole corresponds to some hot theory on the boundary, or form of quantum field theory, and you lower this object, and the distance away from the horizon has to do with the size of the object inside the dual description. So when you lower this object, you get something that's getting bigger and also gets thermalized by the temperature of the black hole. And so the dual description, the other description, is where you have some hot object where you have something being thermalized. And the reason why there is a force, because eventually you want to discover where the force comes from, must have to do with the fact that this object gets thermalized. So this is where I got some of the intuition from to think about gravity more in a thermodynamic way when it has to do with these black holes, but also these realizations of holography. So what I'm going to introduce now is an idea, and this is going to be the original version that I wrote down. It's going to be a refinement of it a little later in the talk. I'm going to introduce the concept of what's called an entropic force, because there are forces that are indeed originating because of thermodynamics. And it's a macroscopic force, so it's something we see at macroscopic scales. And it's basically the consequence of what happens at microscopic scales, but it doesn't really depend on the details of what's happened microscopically. It only comes from a tendency of, well, the microscopic dynamics to increase entropy. As I said, I'm going to reformulate it a little bit later on in terms of phase space, which is going to be a little more general description. But just as an intuition, let's take this entropic force idea, and I'm going to illustrate it with some examples. Actually, entropic forces are not well known in our kind of physics, in the sense that even particle theorists don't use entropic forces. Entropic forces occur in biophysics, for instance. People in biophysics know very well what an entropic force is, because most of the forces they see are actually entropic of origin. So osmosis is one way you can think about an entropic force, because what it actually happens here is that you have particles in osmosis which for an entropic reason want to be on the other side. By entropic I mean they have just more possibilities, more phase space to occupy, and there's a general reason why these particles want to be occupying more phase space, which has to do with entropy. If we then prevent those particles from going there, you'll create a force, which is the osmotic pressure. But the reason for the force is indeed that there's a difference in entropy between a particle being here and a particle being there. And in order to get the force, you have to have a thermal situation where the particles are being moved around a bit so that they explore the phase space. So I'm going to give one other example, which is one which I taught in statistical mechanics class, and this is where I sort of got the intuition from. It's called a polymer. So a polymer is a macroscopic molecule which creates elasticity in rubber, for instance. But the way it does so, it's precisely by an entropic force, because the polymer can be thought of as little rods of those are called the monomers, which can rotate freely, and you can string them together in such a way that each configuration carries the same energy. So there's no energetic reason why these rods want to do anything different than just orient themselves arbitrarily. But when you have a temperature, then because there's simply more possibilities when the polymer is short than when it's long, you create a force because of entropy. And the way it works is if you would pull it out, indeed you see that the polymer has less possibilities because the number of ways that these things can orient themselves is fewer. And so there's a change of entropy, and that creates a force. And I'll write down an equation with sort of the simple equation that I'm going to use in a minute, that if you make a particle attached to this polymer and you move it by a little distance dx, and this is the work you do, it's equal to the temperature times a change in the entropy of this system. It's a little more subtle than this, but anyhow, this is the intuition you can use, is that there's some way in which you use the first law of thermodynamics to calculate the change in energy, and that's related to the amount of work that you do. So an entropic force is induced by change of entropy. So I'm going to think about gravity indeed as such a force, and the reason is as follows. There's some way in which gravity knows about all of the microscopic information that we've forgotten in describing space-time. So at the fundamental scales of our notions of space-time and matter really cease to exist. This is something that I'm going to explain more when I go on. And they're derived concepts. And there's a certain amount of information that I need to forget. And we ignore those degrees of freedom. And when you change the amount of information that you forget, you change the entropy, you change the amount of phase space, and then there's a force. And that force is gravity. So that's the basic idea. And I'm now going to give you a heuristic argument that's going to give gravity from this reasoning. And later on, I'll make more precise what I precisely mean by these sentences. So this is the heuristic argument, and it's going to think about our microscopic world really as just information. Because I'm not going to tell you really what is the microscopic physics, because gravity does not need to arise from any specific description. It's a very generic phenomena, like thermodynamics. So whatever the microscopic laws are, I'm going to think about how to write them down. There's a certain amount of information associated with them, and that information you can think about in terms of bits. That's just a way of thinking about information. I can write everything in terms of bits. So then you get sort of an image like the Matrix movie, where our physics arises from, well, our world arises from some computer, microscopic computer doing all the rules. And then, but this is maybe the way we have to think about physics. The only thing I'm going to put in this is this idea of holography, that the amount of information cannot exceed this area behavior. So I'm going to think about a way of how to get the force from this entropic principle. So you have, I'm going to think about a situation where I eventually put information, replace what I have as our usual description of physics in terms of matter and particles by this information. I'm going to generate a force on that particle there. So the idea is as follows. I'm going to think about storing information, thinking about the microscopic laws as that they're related to information. And whatever that information is, it's written somewhere. And let's just think about them as written on little screens instead of being in space. So this screens, they separate points, and points cannot be defined arbitrarily precisely because of quantum uncertainty. And the argument sort of goes as follows. If I have a particle near the screen and I move it, I want to think about the information on the screen as changing. And that amount of change of information is going to be, say, 1 bit when I displace the particle by 1 quantum wavelength. And 1 bit means 1 bit of entropy and 1 amount of entropy, and I put a 2 pi there for a reason. First of all, I'm going to also assume that the displacement of the entropy, the change in entropy, is going to be linear in the displacement. So the equations that I combined here, I just combine them in one equation because I'm going to say delta S is proportional to delta X. And then I put the inverse Compton wavelength in here. So this may not look like a very familiar equation, but it's an equation you can actually derive near horizons. I'm going to say a little bit more about this. Because I'm going to generate now a force, because I say there's a change of entropy when the particle is moved. If I put a temperature on that screen, I get a force, namely an entropic force. And this is done by that equation. But now if you ask if I have a force, I also have an acceleration. Now I know when there's an acceleration, there's also temperature, and that temperature is given by the Unruh temperature. And now it's going to be clear where this equation comes from, because now I can calculate what the force is. And the force is just going to be F equals ma. So there's a way in which you can think about inertia in an entropic way. And this is the way that inertia arises actually near horizons. So the argument I'm using can actually be used and made precise near horizons, but I would like to put it in a more general context even. So how to get to the gravity? I mean, then I need to have to think about spherical screens, and then you get the same reasoning. The change in entropy I'm going to assume later on, but I'm going to first tell you where the temperature comes from. Namely, there's a number of bits on the screen, and I'm going to assume that this number of bits is proportional to the area. And I'm just going to introduce a constant, which I call g, to express the units of it. So there's nothing assumed yet about gravity. The only thing I want to calculate now is what is the temperature on that screen. Well, temperature you can think about roughly as the energy per number of degrees of freedom. And let's say the number of degrees of freedom is the number of bits. Then you divide the energy by the number of bits, and you get a measure for the energy. For the temperature, I should say. So now I need only one more equation, namely E equals mc squared. And so E is the energy in the system, but m is going to be the mass inside this object. Because now I've written down all equations I need, I'm going to use the same equations I had before, namely for the entropic force and this law of change of entropy in here, because now you can do the calculation quite simply and find a force, and that force is going to be Newton's law of gravity. So Newton's law of gravity can be thought of as being due to the change of information in this way. I must admit, I'm going to say a little bit more about it. This is a reasoning. First of all, I say you can derive near horizons. Actually, what I did is I did the thought experiment that Bekenstein did to arrive at this holographic idea and reversed it. I didn't write down any new equations because all of the equations I wrote down were basically standard equations. I reversed the logic. And there's actually content in changing this logic because there's a certain way in which it tells you that the origin of gravity is the changes in this information. And now this is a heuristic argument with very simple equations, but it really contains the essence. And it needs a bit of a swindle because I'm just reversing the logic. And there's lots of things I'm using here which are not clearly what they are. I mean, for instance, what is the amount of information? Why is it scored on screens? What's the, can it be, I mean, why is gravity attractive? What about other forces? Are there observable consequences? These are questions I'm precisely addressing in the recent work I'm doing, and I'm going to give you a little bit of the hint of where that is going. So that's going to be the next part of the talk. And now this is what attracted the attention in the media, because it's such a simple argument that you can even explain it to a high school student with some knowledge of physics. I should have mentioned, I mean, it's not just this simple Newton law that I can derive in this way. You can do it more generally. First of all, you can do it for more arbitrary mass configurations. Because why would I use a spherical screen? Turns out you have to think about those screens in sort of as equipotential surfaces. And you can also generalize it to obtain Einstein's equations from it. There's some way in which that can be done as well. But there's lots more questions, as I already mentioned. I mean, there's actually some way in which, maybe I should show this, the argument can be changed without changing the result. The result I want to get is Newton's law. But in all of this, I use all kinds of other constants like h bar and the speed of light, and you may wonder, why doesn't that appear in the final law? If I multiply h bar by something else, if I do the same thing here and there, it drops out. The same with the speed of light. So there are all kinds of ways in which these equations may change without changing the result. The main thing I want to convey is not the essence of the reasoning, or the precise formulas, I should say. The essence is that there's indeed a change of entropy, which is the cause of the force, or I'm going to specify more what I mean by entropy, because this entropy is going to be associated not just to information. I'm going to tell you what that information is. By the way, I mean, this is a picture I got from your website. These are calorimeters. And this is one way you can think about this information. This is an edited version of the CMS event, and this is one of Atlas. Because this is precisely how we're going to think about this information. If I think about the amount of information that's inside a certain part of space, I'm going to think about dividing all the energy inside that amount of space up into energy bits. And I'm going to take units of this energy, which are the smallest units you can fit inside a volume. And this is a unit which is basically the wavelength that should fit inside that volume. If you then take your detector, your calorimeter, to have cells which are of Planckian size, and you count all possible ways in which you can distribute the energy over it, you get a number of states. That is the phase space associated with a part of space. And this is actually precisely given the right formulas to get gravity from, and I'm going to connect it even, as I'll show later on, to what we need for dark energy. So if you think about what is the information on the screen, you can actually think about these pictures. So the amount of information that you get from your detector in doing it, of course, it doesn't have Planckian cells, and it doesn't divide up all of the energy in the smallest units, but if you would do it, you find precisely the amount of information associated with a part of space. And I already mentioned the word phase space because this is going to be associated, well, a more precise definition of what this entropy is. So there's a general principle which I'm going to explain now. By first thinking about a very different situation again. Well, it's sort of similar. Here we have two objects in space. They're attracted to each other by a force. And if we would meet such objects, we would describe maybe a potential to describe it. But there may be a very different way of describing this if we would have known about other degrees of freedom. You may say, what other degrees of freedom? What I'm thinking about here is the molecular force between two molecules, two atoms, I should say, like in hydrogen, because then there are electrons which are moving around those nuclei, and the force is being originated because these nuclei, the positions of them, influence the phase space of those electrons. And there's a principle that tells you how to then calculate the force. You can do this in the Born-Oppenheimer approximation by basically solving the Schrödinger equation for the electrons and then generate a force. But we do this in an approximation where we assume that the nuclei move very slowly, and then we can solve it. And then you discover that the force can be calculated exactly like I did for this entropic force. So there's even a way in which this is kind of an entropic phenomena, where entropy now is defined as the volume of the phase space of those electrons. This is a principle. When a fast dynamical system, this is actually something you can do in any setting. So you have some fast variables which you can usually forget about them, because if we think about physics, we usually look at slow variations of objects, but fast variables we integrate out. But if the slow system influences the phase space of the fast variables, there's a reaction force. And when the timescales are widely separated, this force is determined by principle, namely that the phase space volume of the fast variables is preserved. That is actually how a reaction force can be generated. So I'm saying that in our universe we have actually some phase space that we forget about, and we can think about our universe as being filled by some fast dynamical system. And then we can calculate these reaction forces. We can do this in quantum mechanics using the Born-Oppenheimer approximation. And by the way, if you would calculate corrections to this first order, you find things that are involved with gauge fields and so on, so there are even other forces that can originate in this way. But I'm going to think about gravity as being the leading order force in here. And so this is actually a picture of it, because what you use is basically the following, that if you have a Hamiltonian of some phase space variables, which depends on a slow variable x, the eigenvalues of the Hamiltonian vary slowly with x, but they do not cross. This is a theorem you can prove that if you use very slowly, the eigenvalues do not cross. So if you look at the amount of phase space, which is basically counting all of the states up to that energy, it's actually constant. So you use here a sort of a Bohr-Sommerfeld way of thinking about phase space by counting the number of states. And you want to know how this behaves as a function of x. And the principle is that you basically say the amount of phase space volume is constant. And there's some formulas I've given here. I'm not going to describe it in detail, but basically you can integrate over all of the p's and q's up to a certain energy E. This quantity is constant, but that quantity can be thought of as an entropy by taking the logarithm, and then you can calculate the force by taking this constant, and you find exactly the formulas that I had of sort of these entropic forces. So there's a way of thinking about forces, entropic forces, in sort of a Born-Oppenheimer sense, and this is the generalization that I think is relevant for extending these ideas from the horizon, where they're basically thermodynamics, to a space-time picture. You know, this is details. I'm going to say a little bit more about what is the amount of information, or what is actually the indications that there is this other phase space. And this comes actually from string theory. Oh, I'm making noises here. I told you about the ADS-CFT correspondence, and one thing I did in a paper, I'm not sure how to do this now. Oh, here. Hope this better. Is to study the following question. I wanted to study gravitational collapse. So we don't have a black hole yet, but we have something like a neutron star. So what happens in a neutron star is that the fermions, which are, say, you can think about as fundamental fermions, they obey Fermi statistics, and they resist gravity because of the fact that their phase space volume has to be of a certain size. So phase space basically resists gravity. But you also know that once you start adding too many neutrons on top of it, it starts to collapse. So eventually, all of these fermions, they will enter the horizon, they fall on a singularity, and they really are in a point. Now you may ask, what happened to the exclusion principle of those fermions? What happened to the phase space? Well, we studied this question in the ADS-CFT correspondence, and we had to reach a conclusion. There was a certain amount of phase space that we didn't use in this description. There's a certain amount of phase space that's not visible in our usual description of space, time, and matter. I'm going to give you an intuition of that phase space. Because I told you about the Fermi statistics, and Fermi statistics is to do with operations which are exchanging particles, particle 1 with particle 2. And then we can have plus signs or minus signs where they have bosons or fermions. But this is a discrete operation where you just take particle 1 and you exchange it with particle 2. In quantum mechanics, we're used to many other type of situations where we don't think about a particle going to one slit or to the other slit, but we think about linear superpositions. But we don't do this with statistics. Statistics is always a discrete operation where you have the two particles this way or the other way. Suppose you would allow the particle to go into a linear superposition. Suppose you would do this. This is not what we do in statistics, because statistics is just exchanging two particles. But this is, in a certain way, possible. The only thing that happens now is that we don't think about one particle, we have to think about some linear superposition of two particles. This is actually what happens in string theory. When we analyze the equations of string theory, it's close enough, and actually these D-branes that I talked about precisely have this property that you can take linear combinations of them, and that there are degrees of freedom that are added to the whole description. But you can think about it in this way, that statistics becomes a more general equation, namely instead of Z2 where you exchange them, you start rotating them into each other, it becomes a unitary group U2. Or if you have n of them, it's even UN. So what you're adding then is that positions, which are usually just the positions of, say, particle 1 and particle 2, are not just, well, numbers, because there basically can be matrix elements between particle 1 and particle 2. So you're also generating off-diagonal matrix elements. These, by the way, are the open strings, because these are the open strings that stretch between the two. And when we integrate them out, we generate gravity. That already I told you about. And this is precisely because you like to forget about these degrees of freedom. This you can do more generally and think about n particles. And then the n particles, their usual positions are the eigenvalues, say they are on the diagonal. But we generally like to forget about the states that are off diagonal. This is where gravity is sitting. There's a certain amount of phase space that if you integrate it out, you generate gravity. This is standard law in physics, in string theory, I should say, by the way. In string theorists would say, yes, of course, he's just telling us about d-branes, so this is how d-branes work. This is also how gravity emerges in d-branes. So what actually happens when the neutron star collapses is that the modes that were sort of the matter particles on the diagonal, they start occupying the entire matrix. And the black hole, which you then form, should be thought of as being indeed occupying the entire matrix, and you lose the picture of space-time because these matrices don't look like space-time anymore. The space-time indeed must be emerging from the eigenvalues. So now I can even think about my thought experiment, because then I'm saying, well, let's take the black hole. So the black hole, as I told you, is a big matrix, and it has a certain temperature. So this is a big matrix which has a certain temperature. And I'm going to take out one particle and think about what is the force, how the force is being generated on that particle. That one particle is described by one eigenvalue that I take out. But then I have these off-diagonal elements which I like to forget about, which is kind of my phase space that I generally forget. This is where the polar is sitting, and it's this amount of phase space that's causing the force on this eigenvalue. This is the black hole attracting that object. Has to do with this phase space being integrated out, and indeed you can generate an entropic force in that way. So let me now come to the ideas of cosmology and matter. So matter is associated, by the way, with these eigenvalues. Gravity is associated with the off-diagonal modes, but there may be many other degrees of freedom we have to think about. So going back now to the ideas of dark energy and dark matter. So I'm claiming that the reason that we don't understand 70% of the energy in the universe, and we don't really know what dark matter is that we have forgotten about a lot of phase space. Most of the phase space is sitting here. And the way we describe it in our equations, dark energy is just one constant in Einstein's equation. We call it the cosmological constant. But it's 70% of our energy in the universe. There's something happening there. Energy is associated with dynamics. There is a dynamical system associated with dark energy, and there is an amount of phase space associated with it. We have no idea how to write those equations, except maybe what I just described. So, as I said, what went wrong in sort of not understanding is that our current paradigm, where we use matter on space-time and forces, ignores a lot of information, and that's the phase space to be forgotten. And the forces that we see are being induced by that. So I'm going to say something about now where dark energy is sitting. And for dark energy, we have to think about cosmology, and cosmology with a positive cosmological constant. And even here, Hawking played a role because he also computed a temperature for de Sitter space. Namely, it's expressed in terms of the Hubble constant. So if you take the cosmological constant, you can get the present, well, or say the Hubble parameter from that. And then there's a certain temperature associated to that. That temperature plays a role very similar to the Hawking temperature. And I'm actually going to use it in a minute. Actually, there's much more I could say about this, but one thing I can say is that if you now think about the same thought experiment, but instead of, so I should have said the following. This circle here is a horizon. So what happens in the Sitter space is not, well, like a black hole has a region where you cannot see beyond because light cannot escape to us. In cosmology, there's also a certain distance where light cannot get back to us. So if there's a certain positive cosmological constant, there's a certain radius, the Hubble radius, beyond which light cannot sort of travel towards it. So we also have a horizon there. So all of the physics that I talked about near black hole horizons actually occurs in de Sitter space, and it's happening right now. Because there are many things that we can do, like the thought experiments even I talked about, in cosmology. So this is where I want to get to, is namely I want to think about precisely the thought experiments that Bekenstein did of sort of lowering a box towards the horizon and ask what happens to that box. So I'm going to think about this picture because the particles in this box I can think about as matter particles associated, say, with the eigenvalues of this matrix. The horizon is associated with some part, the other part, which is creates a temperature. And this is the part that's responsible for the force attracting it towards the horizon. This is where dark energy is sitting. That dark energy is really in this picture. By the way, I can write down the equations. I wrote down the counting of those states in terms of those bits. It generates a certain entropy. This is the temperature I told you about. If you calculate now what the energy is of the system, you do find the dark energy. So the dark energy is really the energy contained in this dynamical system. And it's sitting there. So I think about dark energy as being part of the matrix degree of freedom, but they occupy also the off-diagonal mode. Matter is what's on the diagonal. But they're really made of the same stuff. This, I think, is most of the space. This is what we see in our ordinary matters. And I think dark matter is there as well, as something surrounding it. And I'll explain this more, because this can be done quantitatively. But this is the idea. First of all, this is just numerology, to be honest. I have not a proof of this, but this is one thing I noticed, that if I think about our universe as being made out most of dark energy is really the equilibrium stuff. There are things that are going out of equilibrium, then you get sort of a Gaussian distribution. Suppose you take indeed a Gaussian distribution where you would say the middle part is dark energy, this stuff is dark matter, and this is the 2 sigma out is ordinary matter, you get sort of roughly the right numbers. And I think this is the correct way, because this is where most of the phase space is sitting, and our matter, our picture, what we describe as physics, our matter that we see and we describe is the thing that's extraordinary. The ordinary stuff is dark energy. And so we have derived our laws of physics by studying this stuff. And this is no surprise that we have no idea how to describe this, because we've been only looking at the tail of it. And this is the reason why we're missing so much of the energy, is that because we're looking at the exceptional things and we're ignoring most of the phase space. And so if you think about cosmological evolution, it's evolution in this entire system where you exchange energy from all of these things. The matter, therefore, need not be conserved. It's really the same stuff. It's going back and forth. It's a very different way of thinking about cosmology and about space-time, because space-time, frankly, I find it very hard to believe that space-time really started this and then blew up and became the entire universe. Something went wrong with phase space. Here I would like to preserve energy conservation, phase space conservation, all of the principles we know in physics, I would like to preserve, even in cosmology. Our current laws of physics, of cosmology, don't obey those. And the reason is that we have been able to write our equations in a form where we have ignored most of the degrees of freedom. So I'm going to do something quantitative, but I'm not going to show you the details because I haven't written it up yet. I'm going to say something about dark matter and a way it behaves inside galaxies. And by the way, there's already an intuition coming from that from here. Maybe I should take this picture. Yeah. I'm going to think about the gravity of the object going towards the horizon. Those are these eigenvalues. I told you that integrating out the off-diagonal modes is generating the gravity here. But this is generating, it has a temperature, and this has some heat bath. That temperature feeds into these modes. And there's some way in which there's a layer in between the matter that's contained in here and the holographic sort of dark energy out there. Actually, this temperature is going to modify the dynamics of these eigenvalues. And I'm going to calculate this by simply doing a very well, back of the envelope calculation. I'm going to say there's a certain temperature. I know what the temperature is. It's this one. I know how many degrees of freedom I have associated with the matter. You can actually write down a number. And I'm just going to do thermodynamics and calculate the effect on the gravity. So I'm going to do something that is going to be related to the flattening of the rotation curves. So usually this is associated with dark matter, and that may still be the case, but the way we're going to think about it here is in a different way. So what people see in galaxies is that the usual Newtonian way in which the matter, where the rotation speeds go down, flattens. And this is kind of a puzzle. And there's actually quite a good way to parameterize this, because first of all, you see that the velocity becomes constant. And then even the constant you get can be understood, well, parameterized in certain ways. And it turns out that you can relate it to the luminosity of the galaxy for many galaxies. But the luminosity is not related to dark matter, it's related to ordinary matter. And indeed, there's a fitting of the function of the parameter. This is a recent paper that does this fitting, where this law is being fitted. You say basically the velocity to the power of fourth is g times the visible matter, ordinary matter, times some parameter, a naught. It's an acceleration. It gives you this curve. Has a number there. By the way, I can calculate this number, and it's basically, it's Hubble's constant divided by 2 pi. If you take this number here, you multiply Hubble's constant with c squared, divide by 2 pi, you get this. And actually, it comes from just thermodynamics. This equation here, and now I'm going to write a plot. You calculate the amount of energy that you get, additional energy in the rotation curves, and you calculate what I would call NKT, the number of degrees of freedom times the temperature. You get this plot over 8 orders of magnitude. And this is just because we're in a regime where gravity is very different from our ordinary gravity laws. It's very weak. It knows about the cosmological temperature. It actually has a scale which is set by cosmology, and there's actually no reason why in a galaxy you would actually expect that the scale set by these rotation curves has a cosmological origin. Here it has an explanation. So there is not just theoretical theorizing which I'm doing. I'm trying to connect to data and to some observations. And for me, this is a very important reason to believe in the ideas that I've been telling you about. And now here I'd like to end. Thank you.
But according to this picture, will the particle physicists find particles that correspond to dark matter, or what?
I must say that I would be disappointed if that would explain the 23%. I would indeed not. But as I told you, one thing I can, and maybe I should go to that picture, one thing I cannot exclude, and actually I've been asked the question, I'm not trying to explain, first of all, why there is, that there's no dark matter. Because I'm telling you there's something happening in the way that, there's some way in which I think about ordinary matter as sitting here. This is what I call dark matter, but it can have components sort of on the diagonal, which I would call ordinary particles. But there's a certain way in which I think the interface between dark energy and ordinary matter has to do with what we call dark matter. And there's a certain way those things are related. I think this is a much more appealing picture because it also tells me something about what dark energy is, and not just think about dark matter as being explained and still be left with the dark energy problem. I think dark energy and dark matter are really part of the same physics, and I have to understand this. And this is why I like this picture much more. But if it would be an ordinary particle and we would be able to sort of explain, it still brings all kinds of questions we know from theory into the picture. The ideas I talked about the emergent space-time and the way we think about gravity in string theory are by now sort of standard law, and they will have an influence, an impact on how we think about cosmology and the early universe. And indeed, I think we'd like to explain, I think it would be very nice if we have not just separate explanations of each component of them, but we understand the entire picture in some form. I mean, there's all kinds of problems associated to this picture. For instance, why are these numbers sort of roughly of the same size? Those are things you would like to be able to explain eventually too. Yes?
What differentiates between dark energy and dark matter? Because there is different properties. In the matrix, it looks like just an 11 in both cases.
Well, of course, you know that the effect is that it's clusters. So there's a certain way in which the energy, that there's a difference between, okay, I'm thinking actually about the dark energy as being the fluctuations on top of the, dark matter as being the fluctuations on top of the dark energy. So the dark energy may define a background, but then there may be fluctuations where there's over and under densities. And this is the usual way we think about dark matter, as being creating over densities and under densities in the energy background. And that's actually sufficient to start generating gravitational collapse and the structure formation that we know about. So it doesn't need to be, for cosmologists, dark matter does not need to be a particle. It's just something that can clump and generate gravitational wells in which other matter can be trapped. And it need not be a particle.
Okay, this may be a very stupid question, but from what I understand, also the space-time, the way we think the geometry of the space-time is not fundamental anymore, like in general relativity, from using this picture. So I was a bit, first of all, is this right?
That's right, yes.
Okay, this is a bit scary for me, but because I was thinking, so usually the striking coincidence in general relativity is that there is a very nice explanation because the mass and all the masses follow the same direction, the same, I mean, the geodesic.
So the equivalence principle.
Yeah, the equivalence principle. Yeah. So in your case, I think it is also there is this thing may be embedded, and is it because the change of entropy also depends on the mass? Is that right, or is completely?
That's correct.
Okay.
So I mean, that's very essential because otherwise the equivalence principle would not be satisfied.
Okay, thanks.
So what happens when we think about our description of the matter and space-time, that's described this part of the phase space. My picture is that there's a dynamics in this entire space where indeed what we now call this part may eventually be part of the rest and the other way around. Our description of what we see now in the far past was a much smaller part of the entire phase space. We basically have been integrating out from here all the way to there, and we only work with the outside. And since there's dynamics between the two, you cannot keep this in a fixed line. You have to shift it, and if you look backwards, the amount of phase space that we have to associate with our matter today have been much smaller. I can explain what are redshifts without having to think about expanding. I mean, first of all, the question was already asked. I mean, geometry is something you want to derive from this. But I think there's just a dynamical system that keeps going, and there's some way in which our laws of physics tell us about how our matter originated from this picture. So maybe the standard Big Bang scenario tells us how ordinary matter has been emerged from the rest. But it may not be the full story, because I think in the beginning of the Big Bang, this part of the phase space was still there. Just what we see originated in some form.
Can you explain why dark matter is not interacting through other forces with ordinary matter in this model?
Well, Well, certainly, I mean, it behaves differently because I'm thinking about it more as a fluctuation on top of the dark energy. And I think, by the way, the dark energy is not something we can localize very closely. So we're not interacting with dark energy in the usual way as we interact with matter. And now, I think it's a detailed question that I would prefer to discuss in private there, actually. Yeah, I mean, I mentioned this, I didn't explain it in the talk, but in the paper I had a way of presenting that, which, by the way, these ideas have already been used before. There is a way in which the equations of general relativity look like thermodynamics, and people have indeed used reverse arguments by saying, well, suppose I use thermodynamics as near horizons as my starting point, then I can derive Einstein equations. So I think there's a way in which these ideas should give Einstein's equations, so in sort of an effective description. So for me, there's a little doubt that eventually when this has been, I mean, this is not a theory yet, I have to really admit, it's an idea. And once you start working it out, it must be clear why general relativity is a certain way coming out of this. But there may be situations where general relativity cannot be applied and where you can compute new effects, and that's actually where I'm more interested in right now. But general relativity should be part of this, at least should be obtained as, I mean, as I said in the paper, I have an argument that shows that you can derive Einstein equations from these reasonings.